There are only three constant things in life: death, taxes, and gravity. Or at least a little bit of it. In this video, we will be talking about gravitational force and some pretty cool things that come out of it. So I think that's really enough for the intro, and let's move on to the actual video. Now, this video will focus on one main formula, and that formula is F is equal to G m1 m2 by r squared. Now, G is gravitational constant. This gravitational constant is about approximately 2/3 times 10 to the negative 11. And you can find out the units by just plugging in the units over here. So we have the newtons is whatever units G in, let's call that U, kilograms squared over meters. And then you do that over here and we expand newtons, so kilogram meter over second squared times meter squared is then equal, and then divided by kilogram squared, and then that's equal to our units after that, which we get kilograms over here, mass on the top, so mass meters over s squared kg. So the units are meters over second squared times kilograms. And there's the units for the gravitational force. Now, m1 and m2 are just the masses of the object, and the two objects, and that's divided by r squared. This law is incredibly important and will serve as the basis for pretty much everything we're going to do in this video. So, now you know that, I need to introduce you to one more thing: Newton's third law. Well, we already covered Newton's third law, but in the context of this, the force, if I say I have two objects here and here, and this is object 1, this is object 2, the force of 1 on 2 is equal to the force of 2 on 1, and just a simple consequence of Newton's first law. Now, often when we have a very small mass, like compared to the Earth's mass, we just say F is equal to G m by r squared. And to that, essentially m is just the mass of the much bigger body, and actually something we will be using to find out a constant that is very important for everyone to know. So I think that's really about it for explaining it. Let me move on to some examples that really show how this works. I've told you about the gravitation at the Earth's surface, little g, around 9.8 meters per second squared. You can also round that to 10. So with that, how are we supposed to know why it's actually there and how it came to be? Well, you're gonna not know the answer to this question no longer, as I'm gonna show you how to find this little g, which is the acceleration at Earth's surface given the radius of the Earth and the mass of the Earth, and also g. But that was given earlier. So let's actually move on to solving this, and you'll realize it's actually pretty satisfying and simple when you think about it. Well, what do we know? We know that we know Newton's second law. F is equal to ma, and the weight of an object is F is equal to mg. So that's for sure going to be one of the formulas we're using. We already have what we're looking for here, g. And what's our other formula that we just covered today? Well, that is F is equal to G times the mass 1 times the mass 2, which I'm doing as a smaller mass, over r squared. And wait, no, this is not G to the power of mm. This is G multiplied by mm over r squared. So there you have it. That's our radius, and I think it's time to get going. So setting these two equal to each other, as at the surface it's going to be after the radius, we're going to have mg is equal to g multiplied by the mass of the object, whatever object's on our surface, it doesn't actually matter, turns out, times 6 times 10 to the power of 24. And then over r squared, so about 6.371 squared. So canceling out the m's and substituting g, big G, we get 2/3, or also times 10 to the 12th, because 6 squared, 2/3 times 10 to the 24th times 10 to the negative 11th divided by 10 to the 12th multiplied by 6 over 6.371 squared. So over here, what we get is we get 10 just to the power of 1. And also, oh, sorry, I got the value of g wrong. G should be to the negative 10th, not the negative 11th. Sorry. So then this becomes 10 to the power of 2, or 100. Then we have 6 over 6.371 squared, which gets us 6 over about 40.58. Now, then we have times, of course, 2 over 3 times 100. Now, we can put the 3 over here. This gets us 2. And then 2 over here becomes 20.29. And then also what you have is, if you divide that by 2, you get around 10.15. So 1 over 10.15 times 100. Now, then, what happens is you divide that. So what you get as a result is approximately 9.8 meters per second squared. And would you have it, that is exactly what we have over here. So that's essentially all we have right there. And as you can see, if you just round some of these masses a little more or do different calculations, you can see how this also rounds to 10 meters per second squared. So that is our first example, and a pretty important example to cover. Our next example will actually be a little more interesting in the way that I haven't really covered it before, but I will show you why it's important and why I really haven't covered it. Number one, because you guys weren't completely ready for it. We hadn't covered this topic yet. And number two, because we proved that in this one, we proved that it doesn't really matter that much. It doesn't really matter which one of these things we use. So without further ado, let me show you example 2. This principle is, this example is saying, prove that inertial mass is equal to gravitational mass. Now, what? There's different masses, but mass is supposed to be a constant. And you're right, and we're going to show how that's true. So, first, let's define these terms. What is inertial mass exactly? Well, this is mass, the mass that resists acceleration. So this is the mass when we're talking about Newton's first law, all objects have inertia. Now, gravitational mass is the mass subject to gravity. So now you know these two terms, and let's go on to proving it. And this is not really going to require much algebra at all. Now, there are two sort of methods to prove this. One is intuitional and one is algebraic. First, I'll explain the algebraic method, then the intuition method. Because I feel like if I show you the algebra method first, you understand the math behind it, and with the intuition method, you understand why that math works. So, well, what do we know? We again know the Newton's second law. F is equal to mi times a. Normally we say m times a, but since all of these Newton's laws of motion deal with mass that resists no motion because of Newton's first law, this means that we're going to use inertial mass. Now, at the Earth's surface, or it doesn't really matter, at the Earth's surface, it's g, etc., but that's the fact. And another formula is again g, m, whatever other mass that is, times the gravitational mass over r squared. Because this is the mass that exerts gravity on the other object, but that other object also exerts gravity on it. So that's that. Now, what we have is we will now plug these equal to each other, because that's what we're going to do. So mi times a is equal to g times m times mg over r squared. Now, again, what's going to happen is, remember, in our first problem when we were doing gravitational acceleration, we found that g was equal to gm over r squared. And it's essentially the same thing, except just with our acceleration. So a is equal to g multiplied by mg over mi times the mass over r squared. So now that we have that, and we know that when you take the mass out, what happens is you get this gm by r squared as your acceleration. So this needs to be equal to 1. So mg over mi is equal to 1. So mg is equal to mi. And that's the algebraic method. Now, let me explain the intuition method. The intuitional method has you realize that in Newton's third law and in gravity, F of 1 on 2 is equal to F of 2 on 1. That means the same object exerting that gravitational force with that gravitational mass is the same object that is being moved with its inertial mass. So, if it's creating that same force with both of those two masses, that means those two masses have to be the same. It's that simple. If I'm the one moving, but I'm also the one being moved, I can't have different masses. Because if I have different masses, either the one being moved will be different, or the one not being moved will be different. And that's the intuitional explanation that shows why this math makes sense. This math makes sense because of Newton's third law. Every force has an equal and opposite reaction. And in reality, these two are opposite forces. It's that simple. So, there is our second example. And if you're wondering what this is called the weak equivalence principle. And is actually a very, very important foundation in general relativity, which was created by Einstein. So, that's really about it for this video today. Thank you so much for watching. If you like this, please make sure to like, subscribe, hit that notification button, and comment down below for more awesome videos just like this. And also, just thank you so much for watching to the end. You guys are really the best part of what I do. And I hope that you are doing really good in your life, wherever you are. And I hope you learned something new for this. So, once again, thank you so much for watching this video. See you in the next one, and bye-bye.